Okay, so lesson 42, now that we've gone ahead, visualized our bivariate data in a scatter plot and fit a line, now we're going to go ahead and use t-procedures to estimate the slope of that line. So instead of just having a point estimate for that slope, we're going to go ahead and find an interval estimate for that slope. So recall, if you had bivariate data on an entire population, so the example we were working with, if we took all students at a small college, recorded their graduating high school GPA as well as their end of year, first year college GPA, you could plot all of them in the scatter plot. So all these purple points, that is the entire population. If you then fit like that line that minimizes the distance to all of the points all simultaneously, this red line, this is my population least squares regression line. So what we calculated from there is, suppose instead of having the entire population at hand, I only have a sample from all of those students. So we took a random sample of 10 students from this small college, took their high school GPA and their first year college GPA, and calculated an estimated least squares regression line. So y hat tells me this is estimated using sample data. The letter B, so B0 and B1, this tells me, hey, these are sample statistics. So B0 estimates beta 0. B1 estimates beta 1. So whenever you see Greek letters, it should make you think, oh, this is a parameter. So these are, I have mu of y is equal to beta 0 plus beta 1 x. That is the population line. Every single thing here with the Greek letters, it should scream that this is from the population. But notice that it totally, the line that we estimate from our sample totally depends on the sample we collected, right? I took a random sample of 10 students. If I took another random sample of 10 students, I might come up with a different least square regression line. So for example, I go ahead and I sample again, and here's my least square regression line for sample 1. So sample 1. I take another sample of 10 students. So this is sample 2. I take another sample, sample 3. And so what we're doing here is showing that from sample to sample, if you look at my y-intercepts and you look at my slopes, they fluctuate. So from sample to sample, especially we're focusing on the slope fluctuates from sample to sample. So it's estimated to be 1.07 for my first sample, positive 0.68 for the second, positive 0.78 for the third. This is the one we were using earlier in the earlier lessons. So the idea is from sample to sample, our slope that we calculate using sample data can fluctuate. So this B1 is a sample statistic. And because it's a sample statistic and we know things like we assume that it's normally distributed and all that, we can calculate a confidence interval for that slope value. So what I want to conclude here is every sample can calculate own least square regression line. So you can get many, many different least square regression lines if you take many, many different random samples. So here's what we mean. So this red one, and I hope you can see the red okay, is our population line. And all these different blue ones, these are where I took random samples of 10 and calculated the line. And I did it many, 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 many times. So as you can see, the values that we estimate for the y-intercept as well as the slope, they're random variables. They fluctuate from sample to sample. The observations I get in sample 1 can differ from sample 2, so my estimated least square regression line will change from sample to sample. So we do know, though, that these estimates that we calculate with our sample data, they are unbiased point estimates for the actual like population y-intercept and population slope. So on average, if I were to repeatedly sample, take all samples of 10 and calculate all the least square regression lines for all of them, on average, I'm hitting 0.67 for the y-intercept and 0.77 for the slope. So now we're looking at t-procedures for confidence interval for beta 1. So beta 1, be very, very careful about the subscript. We will be particular about this one. So, so we want to estimate the slope from the population, the average change in y with a change in x. Note, most of the time, if we have context, we're going to put it here. So here, if we want to estimate beta 1 with the GPA example, we want to estimate the average change in college GPA observed when we have a change, or usually an increase of 1 in the high school GPA for all students at this small college. So my conditions. This first condition should always look familiar. There's never going to be a time where we don't want that to be true. Statistics is honestly really hard to move forward if you do not have a representative sample. Typically, the easiest way to do that is to take a random sample. It's possible to have representative and not random. It's a lot harder though. So then we were just introducing the residuals need to indicate that the 4 conditions of inference are met. So we need to know that median align was appropriate. So we need to know that the linearity assumption is met, the observations are independent from one another, that the normality assumption is met, so that if you look at the points around the line, they're roughly normally distributed around the line, and constant variance, so the spread around the line at any point in the line, it's roughly the same. And then this is not so much a condition so much as we prefer to have a larger sample size. It is really, really preferred. 10 is not our preferred sample size, but it's easier to break down and do things by hand if it's smaller. Typically though, we have R. It's not going to really impress a whole lot of clients if you do all this math by hand most of the time. Just a note. So when we go ahead and we want the confidence interval for the slope, our point estimate is going to be B1. So B1 is going to come from our output, or maybe hand calculated, probably our output, times T star. So we're going to have to use the T table or R again to find our T star critical value. So we have to find for our degrees of freedom, so n minus k plus 1. So it's n minus 1 like by default, so n minus like, but then minus the number of explanatory variables that you've added. If you only have 1, there you go, there's 1 quantitative. So then times your standard error of B1 is this gnarly, gross looking equation. This is not something we calculate by hand. This is not something we will typically ever ask anyone to calculate by hand. R will calculate this for us. It makes our life so much easier. So please, please do not try to force this to happen. That is super gross. R will give you the standard error for B1 in the output. It is much easier to just pull out of the output, since that's usually where you're getting B1 as well. So here, so this is my y-intercept, so this is B0. The standard error, there's the standard error for B0. And so then explanatory variable, so what will be there is the name of your explanatory variable. So like in ours, it would say high school GPA, something like that. And this is the slope that goes with that explanatory variable. And then this is the standard error. So ultimately, we will never really focus on this. It's very rare that you actually test the intercept. The intercept is usually useful to have. It's usually weird to remove it. So this is the line that we're really, really interested in here. So looking at my output, so this is this is B naught, this is B1. So B1 is that 0.7758. Standard error for B1, so standard error, just line up here. It's going to be 0.1937. And then my degrees of freedom is going to be my sample size minus k plus 1. So it's going to be 10 minus, I only have one explanatory variable, high school GPA, and it's quantitative. So 1 plus 1, so 10 minus 2 would be 8. So I'll use that on my next slide there. So here's my estimate for B1, here's my standard error here, and I want, so my degrees of freedom are 8, and I want so from the random sample of 10 students, calculate and interpret, that's not quite a word, huh? 95% confidence interval for the true change in college GPA given a 1 unit increase in high school GPA. So degrees of freedom 8 tells me which row to look at. So I'm going to look at this 8 row. The 95% confidence tells me which column to look at. I like to look at the bottom and go, oh, 95. So where they line up, this means that my T star, my critical value that I'm going to use is 2.306. I do not want to use Z star because we do not know the population spread at all. It's really, really unlikely that we do. So here, I'm going to have B1 plus or minus T star times standard error, B1. So for here, my estimate for the slope was 0.7758 plus or minus 2.306 times my standard error 0.1937. Then I'm going to get 0.7758. Absolutely, please run through this math yourself. Every once in a while, I make an error, either just writing down the wrong number or doing the math. Absolutely check. I'm only human. I'm definitely not doing this math in my head right now. I'm not that good. So then from here, I get positive 0.3291 to 1.2225. So I went 4 places past the decimal. A lot of the times that's pretty standard for me. So we'll get into interpreting these more, but we're saying, hey, for a 1 unit increase, so a 1.0 increase in high school GPA, the 95% confidence interval estimates that the college GPA increases, because this is positive, by 0.33 to 1.22 increase with a point estimate of a 0.78 increase. So that would be our interpretation there in context. It's quite literally combining the confidence interval format with the how to interpret a slope format. So I know I've definitely starred both of those slides. Take a look at them. Next, we're going to do a t-test for that slope. And just even testing, is it even useful to have this explanatory variable?